Good morning, children. Hope you all have gone through yesterday's videos. We have been discussing on the regulatory mechanisms, the energetics, how many number of ATPs are produced when one molecule of fatty acid and even chain fatty acid is undergoing beta oxidation. How many huge number of ATPs can be produced even from a single molecule of a fatty acid, right? So energetics we have completed. Regulation we have over. That is, there are two mechanisms of regulation, either by means of allostric regulation or by means of covalent modification, right? The allostric regulation is controlled by modifiers, which includes activators and inhibitors. So there are two enzymes which are subjected for regulation. One is the CPT1 or CAT1, and the other enzyme which is involved in the regulation of fatty acid oxidation, beta oxidation of fatty acid, is the acetyl-CoA carboxylase, which actually comes under the synthetic pathway, right? So synthesis is also having an influence on the oxidation or the breakdown, right? So it is the acetyl-CoA carboxylase enzyme, which is the rate limiting enzyme of the fatty acid biosynthetic pathway, is responsible for deciding whether the breakdown has to be initiated, synthesis has to be stopped. So it is the acetyl-CoA carboxylase which decides whether the beta oxidation has to be initiated or not. Clear? So for that, there are different types of modifiers are there, like free fatty acids in the circulation, the citrate level, even the carbohydrate metabolism can influence the fatty acid oxidation. So whenever there is citrate level in the body, increased citrate level, citrate level kuda, whenever there is carbohydrate abundantly present in the body. So increased amounts of glucose can lead to increased amounts of citrate. So this elevated levels of citrate can block the beta oxidation, right? They inhibits the beta oxidation. How? By influencing the malonyl-CoA. How is the malonyl-CoA found? Malonyl-CoA is found by the carboxylation of acetyl-CoA by the enzyme acetyl-CoA carboxylase. So this malonyl-CoA is always acting as a inhibitor for CAT1, right? So that is how the regulation is happening in the case of allostric modification or allostric mechanism. The second one is the covalent modification. Covalent modification involves the action of hormones, and the most important hormone involved in the beta oxidation, involved in the regulation of beta oxidation, is the glucagon and adrenaline, which are the anti-insulin hormones. So whenever there is an energy demand, whenever there is a mitochondrial NADH to NAD ratio is reduced or reversed, what happens? Then the beta oxidation will be initiated. So glucagon acts. It goes and binds to the receptor. It activates the adenylate cyclase enzyme. Cyclic AMP will be formed. Cyclic AMP activates protein kinases. Protein kinases converts the inactive TG lipase to active TG lipase, so that TG is undergoing breakdown. So the more and more free fatty acids will be liberated into the hepatocytes or liver or muscle, adipose tissue, etc., so that the fatty acid can be oxidized. Clear? So that was the regulation. Now we are going on to the beta oxidation of short chain fatty acids. So we have completed the beta oxidation of a long chain fatty acid if it is having an even number ranging between C12 to C18 or C16. Right? So C12 in C18 or C20 fatty acid, how is it broken up in the various tissues of the body? That's beta oxidation. So beta oxidation yields what? If you are having a 16 carbon palmitic acid, palmitoyl-CoA will be formed first. This palmitoyl-CoA is translocated from cytoplasm to matrix with the help of carnitine. Then in the matrix, it is subjected for beta oxidation. Each cycle of beta oxidation has 4 reactions. There are 2 oxidational reactions catalyzed, one by FADH and the other one is by NAD. Then there is one hydration reaction, which is a step 2. And there is a thiolytic breakage, resulting in the reduction of the carbon chain by 2. 2 carbon atoms will be removed at a time, and that 2 carbon atoms are released in the form of 1 molecule of acetyl-CoA. So if 1 molecule of 16 carbon palmitic acid is subjected for beta oxidation, we will get 8 molecules of acetyl-CoA through 7 cycles of beta oxidation. Along with that, we get 7 number of FADH2 and 7 number of NADH. So a total of around 129 ATPs, or exactly speaking 106 ATPs will be obtained when 1 molecule of palmitic acid is subjected for beta oxidation. So that is a even numbered oxidation. even numbered carbon chain or fatty acid oxidation. Now, there is a slight difference if there is a shifting from the even to the odd chain. So, there are dietary sources which can contain odd chain fatty acids. Of course, the diet primarily contains even chain carbon atoms, long chain fatty acids which are having even numbered carbon atoms. But there are sources, there are diet which contains, which are rich in odd chain fatty acids. A typical example is cow's milk, pashuinte paal. Pashum pala contains rich amounts of odd chain fatty acids. So, is there any difference between the beta oxidation of even chain and odd chain fatty acid? Of course, all the reactions are the same except for the final product. In the final cycle, last step of the last cycle, we'll be having a slight difference in that we are having each cycle ends up in the formation of acetyl-CoA. But when we reach the last cycle, last round of beta oxidation, instead of acetyl-CoA, the product obtained will be propionyl-CoA. Okay, so what happens to this propionyl? Because 17 carbon ആണ്. But as usual, 16 carbon ആയിട്ടുള്ള palmitic acid എങ്ങനെയാണോ oxidize ചെയ്യണം അതേപോലെ തന്നെയായിരിക്കും ഒരു 17 carbon ആവുക. So it will be having 7 cycles of beta oxidation, 7 rounds of beta oxidation take place with the liberation of 7 molecules of acetyl-CoA and 1 molecule of propionyl-CoA. അപ്പോൾ ശരിയായില്ലേ? 7 2s are 14, 14 plus 3, 17. Okay. So that is how the oxidation of an odd chain fatty acid will be taking place. In 19 carbon fatty acid ആണെങ്കിലോ അപ്പോൾ എന്തുണ്ടാവും? എത്ര cycles ഉണ്ടാവും? There will be 19 ആണ്. അപ്പോൾ suppose 18 carbon ആണെങ്കിൽ എന്താ സംഭവിക്കുമായിരുന്നത്? We will be having -1 ആണ് വരിക. Number of cycles will be 8 2s are 16, 9 2s are 18. So there will be 8 rounds of fatty acid oxidation, beta oxidation നടക്കും and 8 rounds നടക്കും. 7 roundilum we'll be having acetyl-CoA molecules, right? That is 7 2s are 14, 7 alla 8 rounds. 8 2s are 16, 8 2s are 16, 16 plus 3 19. The last one will be what? The last round of beta oxidation will be yielding 3 carbon propionyl-CoA. About 16 plus 2, 19 carbon atom. Okay, so that is how the beta oxidation of fatty acids will be taking place. Now, acetyl-CoA, what's the fate of acetyl-CoA? Acetyl-CoA thus formed will be entering into TCA cycle and it liberates ATP molecules. One molecule of acetyl-CoA can give 12 molecules of ATPs, right? So, in that we have calculated the energetics, right? But what is happening? What is the fate of propionyl-CoA? Can propionyl-CoA enter into TCA cycle? Propionyl-CoA as such cannot enter into TCA cycle, but propionyl-CoA undergoes some sort of chemical changes so that some chemical reactions happen, some changes happens to the structure of the propionyl-CoA so that it gives rise to a TCA cycle intermediate. Okay, so it can bring about a formation of a TCA cycle intermediate, and again it is effectively utilized by the body. Otherwise, what happens? Propionyl-CoA use ചെയ്തിട്ടില്ല എന്നുണ്ടെങ്കിൽ what happens to it? The propionyl-CoA ഞാൻ പറഞ്ഞു ബോഡിയിൽ ഒരിക്കലും waste product accumulate ചെയ്യാൻ body will not permit. If there is accumulation of any waste product, it will be immediately released through urine. Urinary excretion അവിടെ നടന്നുകൊണ്ടിരിക്കും. Clear? So it's not a normal condition. It will be an abnormal condition. So body 3 carbon atoms ആണ്. അതൊരു ബോഡിക്ക് ഏറ്റവും precious ആയിട്ടുള്ളതാണ് ഈ organic compounds ഒക്കെ. അതുകൊണ്ട് തന്നെ the body will not allow the simple excretion of propionyl-CoA. The propionyl-CoA thus formed will be effectively utilized by the body. നമ്മളിപ്പോൾ glycerol ആണെങ്കിൽ glycerol immediately എന്താ ചെയ്യുക? glycerol 3 phosphate ആയിട്ട് convert ചെയ്ത് again it will be reutilized. Body ഒരിക്കലും ഇങ്ങനത്തെ carbon atoms, organic compounds ഒരിക്കലും waste product ആക്കിയിട്ട് excrete ചെയ്യാൻ it won't allow. It will be effectively utilized by the body. In somehow it manages to get converted to some useful products. Clear? So the same way, propionyl-CoA also will be undergoing some sort of chemical reactions so that it will be effectively utilized by the body. It won't be getting wasted out. Okay, so what are the chemical reactions? What are the chemical changes happening to propionyl-CoA? What happens? See, this is a propionyl-CoA. So see, there are 3 carbon atoms, right? So CH3, CH2, COOH. COOH we call this propionic acid. So OH remove it, SCO ആയിട്ടാണ് വന്നിരിക്കുന്നത്. So it's known as propionyl-CoA. Now what happens to propionyl-CoA? Propionyl-CoA undergoes a carboxylation reaction by means of an enzyme propionyl-CoA carboxylase. See, in presence of propionyl-CoA carboxylase, see who is coming? It's a bicarbonate ion. Bicarbonate ion വന്നിട്ടാണ് carboxylation നടക്കണമെന്നുണ്ടെങ്കിൽ who will be the coenzyme? It will be the biotin. So in presence of biotin, propionyl-CoA carboxylase undergoes carboxylation reaction so that it will be converted into another compound known as D-methyl malonyl-CoA. Right? So D1, 2, 3, 4. Right? So 4 carbon atom ulla a compound item mari. And the compound is known as methyl malonyl-CoA. Now, D-methyl malonyl-CoA body ki utilize cheyan pattilla. So it will be converted. It undergoes racemization. അല്ലെങ്കിൽ it undergoes conversion. DL conversion. DL isomerism avada nadakkum. That is known as racemization. To give rise to L-methyl malonyl-CoA. Clear? So that is a change happening. D-methyl, the position of the methyl group will be getting shifted. ആദ്യം CH3 ശരിക്കും ലെഫ്റ്റ് സൈഡിൽ റൈറ്റ് സൈഡിലായിരുന്നു, അത് പിന്നെ ലെഫ്റ്റ് സൈഡിലേക്ക് മാറും. അപ്പൊ നിങ്ങൾ എഴുതുമ്പോൾ ഈ CH3 ശരിക്കും മേളിലേക്കാണ് ഇൻഡിക്കേറ്റ് ചെയ്യേണ്ടത്. ക്ലിയർ? ഈ മിഥൈൽ ഗ്രൂപ്പ്. റൈറ്റ്? അപ്പൊ CO മൈനസ് CH3 CH CO SCOA. D-methyl malonyl-CoA. ഇവിടേക്ക് വരുമ്പോൾ CH3 താഴത്തേക്ക്. റൈറ്റ്? അതായത് താഴത്തേക്ക് എന്നുള്ളതല്ല, ഇത് ബ്രോക്കൺ ലൈൻസ് എന്ന് പറഞ്ഞാൽ വാട്ട് ഡസ് ഇറ്റ് ഇൻഡിക്കേറ്റ്? ബ്രോക്കൺ ലൈൻസ് ഇൻഡിക്കേറ്റ് ദാറ്റ് ദ CH3 ഈസ് അവേ ഫ്രം us. നമ്മളുടെ അടുത്ത് നമ്മളെ എല്ലാം ഫേസ് ചെയ്യണമെന്ന് കാണിക്കാനാണ് ഈ ബ്രോക്കൺ ലൈൻസ് വെച്ചിട്ട് അവിടെ ഇൻഡിക്കേറ്റ് ചെയ്തിരിക്കുന്നത്. അതേസമയം ഈ ബോണ്ട് ആയിട്ടുള്ള സ്ട്രോങ് ആയിട്ട് അല്ലെങ്കിൽ ബോൾഡ് ആയിട്ടുള്ള ഈ ബോണ്ട് ഇൻഡിക്കേറ്റ്സ് ദാറ്റ് ദിസ് CH3 ഈസ് ഫേസിങ് us. CH3 നമ്മളെയാണ് ഫേസ് ചെയ്യണമെന്ന് കാണിക്കാനാണ് ഈ ബോൾഡ് ആയിട്ടുള്ളത്. ഇവിടെ കണ്ട H broken lines ലാണ് ഇൻഡിക്കേറ്റ് ചെയ്തിരിക്കുന്നത്, which shows that H is away from us. It's on the other side. Clear? 3D ആയിട്ട് നോക്കുമ്പോൾ H അങ്ങേ സൈഡിലും CH3 നമ്മളെ ഫേസ് ചെയ്തിട്ട്, അതാണ് D ഫോം. L ഫോമിൽ വരുമ്പോൾ നേരെ റിവേഴ്സ് happens. H will be facing us and methyl group will be facing away from us. Right? So അതാണ് difference between D and the L forms. So D-methyl malonyl-CoA is converted into L-methyl malonyl-CoA by racemase enzyme. It's only an isomerism. D form and L form like mari. Now what happens? It now undergoes some sort of positional changes. ഇതൊന്ന് റീഅറേഞ്ച് ചെയ്യും. ഈ സ്ട്രക്ചർ ഒന്നങ്ങ് റീഅറേഞ്ച് ചെയ്യും. ഇവിടെ നമുക്ക് CO മൈനസ് C ഓരോ കോർണേഴ്സും ഇൻഡിക്കേറ്റ്സ് പ്രസൻസ് ഓഫ് കാർബൺ ആറ്റംസ്. ഓക്കെ, അപ്പം COO മൈനസ് CH CH3 CO SCOA. Right? So this is undergoing some sort of rearrangement so that COO minus either CH2. E carbon one more borrows one more hydrogen atom from this methyl group. Right? Above either per side chain atom. This side chain marita, it forms part of the backbone. Clear? So it's having some sort of rearrangement. And this rearrangement is carried out by an enzyme known as mutase enzyme. Mutase enzyme converts L-methyl malonyl-CoA to succinyl-CoA. We have heard this term, no? Succinyl-CoA. Where does it come? It comes in the TCA cycle. So succinyl-CoA is a TCA cycle intermediate. Right? So this is how in the TCA cycle we can have we can have our TCA cycle. So propionyl-CoA is not getting wasted up. Instead, it is entering into the TCA cycle. Right? So it's a it can form as the non-carbohydrate source in the glucose formation like പോവാണ്. So it is a gluconeogenic substrate. നമ്മൾ gluconeogenesis എടുത്തപ്പോൾ different substrates are there. Non-carbohydrate amino acids ഉണ്ട്, propionyl-CoA ഉണ്ടെന്നൊക്കെ പറയുന്നു. അപ്പൊ എവിടുന്ന propionyl-CoA എന്ന് അന്ന് ഞാൻ പറഞ്ഞു fatty acid oxidation വരുമ്പോൾ I'll explain. Right? I think you remember it. So propionyl-CoA is coming as a result of beta oxidation of odd chain fatty acids. From where does you get the odd chain fatty acid in your body? The one of the major sources is cow's milk. Cow പശുവിന്റെ പാലിൽ നിന്ന് നമുക്ക് കിട്ടുന്ന ഒരു one of the fatty acid is the odd chain fatty acid. So it has to be digested and absorbed and can be utilized. It is by means of beta oxidation of odd chain fatty acid resulting in the formation of 7 molecules of acetyl-CoA and 1 molecule of propionyl-CoA. The propionyl-CoA is not allowed to get wasted up. Instead, it enters the TCA cycle. So it is acting as a gluconeogenic substrate. Okay. So the enzymes are carboxylase enzyme. Right? Carboxylation happens in presence of biotin. Then racemase enzyme converts D-methyl to L-malonyl-CoA. Then L-methylmalonyl-CoA is converted into succinyl-CoA with the help of mutase enzyme, and the mutase enzyme functions only in presence of vitamin B12. It's very important, vitamin B12.